this hour, you have probably heard that in the previous weeks there was an announcement about the evaluation of the gravitational waves. And if you would ask my personal opinion on what was the two most important discoveries in my lifetime, I would talk about the most important discoveries. I would say two of them. One is the mass of the neutrino, and that might turn out to be a boring discovery depending on the properties of the neutrino. The other most important discovery in my lifetime has been this gravitational waves. Now, gravity is not something that we understand. We don't really understand how it works. So now we have a new measurement about the properties of gravity, and we don't know what it can do, but hopefully it will help us understand gravity at a new level. I'm not an expert on gravity, so we already have an expert in our department. So I kindly ask Brigitte to give us an overview for the first year students on what are these gravitational waves, why are they important. I also would like to say a few words about Byron. Most probably you will take a course from him eventually. If you don't take a course from him, I mean, you should not go away from this department without creating some excuse to discuss something with him. And at some point, I would most of the students they feel ashamed of knocking on their professor's doors. I had a nice advice from my photography teacher. He used to say that the ones who learn the most are the ones who are shameless. So you should be shameless and knock on his door to discuss at least something about physics. You should find something to discuss with him. Okay, so thank you, Byron, for something to give this talk.
Okay, Altu, thank you very much for the nice introduction and the opportunity to talk to freshman students, which I have not done for a long time, okay? Well, you have already learned Newtonian mechanics, gravity in Newtonian theory, so that means you must be excited about, how gravity works. So I will tell you, talking about it. Ya böyle bağırsam duymaz mısınız? Daha mı iyi? Altu, ben böyle yapacağım bu işi. Okay, I don't know how to do that. Well, okay, so here is the thing. First of all, gravitational waves, which were conjectured to exist, like 100 years ago, were observed, okay? So this is, as scientists, you should understand that this means, well, we are not scientists yet, but that really means the following. Scientific fact essentially comes with some kind of probability, right? So what is the probability that these people have observed the gravitational waves? Well, they are so confident. So it always comes with some kind of caution, but you have to know, because I'm telling you this because some people ask, did they really find gravitational waves? Now, what does that mean? Do you really exist? Prove it to me that you are not in my dream right now. Prove it to me. It's not possible at all. So you have to be very careful. What we know is that these people actually have shown that they could be wrong with this probability. Okay, 1 over 3.5 million. That means scientifically, we call it 5 sigma. Scientifically, they have observed gravitational waves. That is something you have to understand. In the near future, this will be increased to actually better accuracy. So that's important. Now, another thing is, what are these gravitational waves, first of all? And secondly, why are they important? And perhaps, thirdly, why did it take so long to actually show that they exist? Well, Altu said something very, very interesting. One of the most important observations in his life, which is around 40 years, is the observation of gravitational waves. Okay? Well, that is actually correct for me also. This is one of the most exciting things I have seen in my life. The reason is the following. I didn't expect, actually, these people to show that there are gravitational waves. That is the amazing thing, because this is a very, very interesting piece of experiment. And I was thinking, in 20 years, when I am around, if I live 60 or something, then I will probably hear that they will be measuring these gravitational waves. This is rather amazing, okay? So, amazing piece of, human knowledge, engineering, physics, mathematics, geometry and everything being executed. So we should all be proud, sort of, as human beings, being able to detect this. Now, what was detected was the following. Listen very carefully. 2 black holes, and I'll tell you why we believe in that. 2 black holes, 1.3 billion years ago, collided, okay? And then they distorted the space, basically. And this collision today, well, this year was observed on Earth. And from theory, we can tell exactly what happened. So what happened here is the following. First, let me give you the facts, and then later on, I will tell you how this works. So there are 2 black holes, and I will tell you what a black hole is. Close to each other. How close? This is Ankara, this is Afyon, okay? That close to each other. Well, a little bit more than that. Actually, this is 350 kilometers, so 100 kilometers more than that. What are the masses of these black holes? Together, it is like 60 million times more massive than the Earth, okay? 60 million. So each one of them is around 30 times the mass of the sun. So huge objects, they are really dense, and they rotate around each other with a speed about 0.6 times the speed of light. That means these guys are rotating around each other like 75 times in every second, okay? 75 times in every second. Now, I'm telling you about the last 0.2 seconds of their life. So in the last 0.2 seconds, this is the thing that we can construct. So they have been doing this for millions of years. They are losing energy, and I'll explain that. They are losing energy, and that's in the last 0.2 seconds, they can create a lot of distortion in the space-time, and that can propagate through the universe, and then it comes to the Earth. It actually stretches the distances, so the distance between any points, like my height, okay, changes 75 times in a second. It actually increases and gets back, basically. And then if you can measure that, you have proven that something passed. Now, if you hear the signal, you can actually hear the signal. It's like this. Jick. That's it. Well, for 0.2 seconds, that is what the experiment heard. It's called chirp, cıvıldamak. That's what it is. Jick. That's it. And from this, they can construct what happened back then, okay? It's amazing, because just like any waves, when you talk on the phone, you know that what you are doing is accelerating charges, right? Electric charge is accelerated. Accelerated electric charge gives away energy in terms of electromagnetic waves. It propagates from one point to another point. And accelerated mass, Albert Einstein showed that if you accelerate mass, it actually gives away energy in some form that I will explain. What is amazing is in the last 0.2 seconds of this collision, the energy released is 3 times the mass of the sun, which is 50 times more than the total power in the universe coming out of all the stars. So amazing. If you want to convert it to these light bulbs, I have calculated that. So in the last 0.2 seconds, around this many light bulbs of, let's see, 36 watts. That's a lot of light bulbs. So huge energy actually is emitted in this collision. It's not visible light, okay? Visible light, that's a different story. So listen to me. What is going on here? What's going on is exactly the following. You have learned from Newtonian theory that when you have two masses, they attract each other. This is an observation that Newton made a long time ago, right? So you have a mass here, you have a mass here, M1 and M2, and Newton's observation was that they attract each other, okay? Now, according to Newton, there is no such thing as gravitational wave because of the following. If you look at this, this says nothing about the motion of these masses. For example, if this thing is rotating, this doesn't change, okay? If it is moving like this, it doesn't change. If it is like shrinking, it doesn't change. Well, it changes, but instantaneously, actually. Instantaneously. We have to be careful. Let's say some part of this thing is actually converted to some kind of energy. Immediately, this guy actually knows about that. So you can imagine the following. The sun is like 150 million kilometers far away from us. If something happens to it right now, let's say it disappears, okay? Then, according to Newton, we just know it right now. But this is not consistent with special theory of relativity. Special theory of relativity says that no information can travel faster than light. So gravitational information must at most travel with the speed of light. Gravitational information. That means if I move here, in a little bit later, the gravity that I actually create over there will change in a little bit later. That is what is gravitational radiation. Why? Because the field will change there, okay? But it does not exist in the Newtonian theory. Now, this formula is a remarkable formula. It works fine, but the problem with this formula is, yes, it doesn't obey special theory of relativity, and it doesn't explain some other things. For example, it doesn't explain the motion of Mercury around the sun. The planet Mercury has a weird motion. It is not a closed orbit, okay? Each year, actually, the closest point of Mercury close to the sun moves a little bit further. There is no way to explain this within Newtonian theory. And eventually, you need general theory of relativity to replace this somewhat approximate theory. And general relativity theory, when you actually do it carefully, it turns out it is not a theory of forces. It is a theory of space-time, essentially in the following sense. And this is what Albert Einstein found out, which is rather amazing. So what he says is, what you call gravity is essentially the following. You have a mass, energy, pressure, all those things, actually. When you put it in space-time, this space and some time, t, let's say, it changes the structure of the space-time. We don't see the space-time. Take out everything in this room, we don't see what is left. But Albert Einstein says that this is something physical. You know, if you take out everything, what remains is a physical, dynamical object which is affected by gravity. How is it affected? Well, it is affected by the following. If there is a lot of energy, any kind of energy, the space-time is actually curved, in the sense that if you take this point and this point, if it is not curved, the shortest distance between them is a line. But if it is curved, it is actually some kind of curve. So particles follow the shortest distances between points, and that's how gravity actually works. For example, you might know that on the face of the Earth, so you are very close to, let's say, the face of the Earth. This is like around 6,500 kilometers. So when you are trying to fly from Turkey to Japan, right, let's say, the shortest path turns out to be over close to Siberia. Why? Well, I mean, if you do it carefully, we call it geodesic, okay? The circle that passes through the center of the Earth. So the first thing we learn is that there is something else other than Euclidean geometry, and apparently it turns out gravity has something to do with the dynamics of space-time, okay? With this picture, Albert Einstein actually showed that the sun, which is the most, let's say, massive object in our solar system, essentially, it is rotating, right, a little bit. It curves the space around. So I have to show it somehow to you. It curves the space, let's say, like this, let's say, okay? And the Earth here, for example, with initial velocity given by initial conditions in the beginning of the solar system, is moving around this curved space, thinking that it is following the shortest path. Yes, it is following the shortest path, okay? So in this sense, what we have is Einstein takes out the force in gravity and then says, basically, the particles obey just the paths, okay? For example, in this room, we are actually not following the shortest path because of the following reason. There is the Earth pulling us, okay? And this is falling down, doing its natural thing, but there is a force, because you are sitting, there is a force, external force, stopping you from falling. So there is an external force. When there is an external force, you can stop, actually, the motion. Essentially, without any external force, the particles obey just like Newton's, zero acceleration case. When there is no force, acceleration is zero, right? Newton says when there is no additional force or thing than gravity, the particles obey a curved space. So in some sense, Albert Einstein did something rather remarkable. If you recall from Newtonian physics, you learned that if you are inside a car going with acceleration A, right, and you have to do physics inside a car, you cannot, let's say, go out, then you need to put additional forces, right? Fictitious forces to explain the appearance, the motion of objects, okay? Just like this, Albert Einstein showed the following. In the presence of gravity, essentially, in the presence of gravity, well, the gravity is pretty much like, well, if you choose correct coordinate system, I will explain what it is, you can get rid of gravity. You don't have to include additional forces. It is like this. You are in an elevator, okay? You are in an elevator, and then somebody cuts the elevator, right? You all fall. Everybody falls. Everything falls. Einstein says that during this fall, you do billions of experiments with everything you like, you will not be able to detect the presence of gravity. So in some sense, gravity is a fictitious force. Okay? This is important as I will come. It's rather amazing. So you can get rid of gravity. You can get rid of gravity if you choose correct coordinate system. And what is the correct coordinate system? You fall with whatever falls. Okay? Amazing observation. But what is that good for? I know that there is gravity, right? So it turns out, according to Albert Einstein's theory, gravity actually is a tidal effect. Tidal. What does that mean? You know the tidal forces, right? Here is the Earth. It is covered with oceans. Here is the moon. Okay. So every 12 hours, because the Earth is rotating, right? Every 12 hours, the moon is actually attracting this part of the ocean more than this part of the ocean. Because of the difference between these two forces, there are tides, tidal waves in the ocean created. Okay, this is an example of actually gravity. The difference between the force difference between these 2 points is what we call gravity, essentially. Okay, now imagine this at a very, very, very small level. So, if this is the Earth, okay, let's make the Earth like this. If this is the Earth, if you take 2 points really close by points, what happens is that they will fall like this, okay? So, from the way they move, actually, you can detect gravity, essentially, okay? If there is a difference between them, you can actually follow their geodesic and find out that there is something called gravity. So, it turns out we cannot detect uniform gravity, but we can detect changing gravity, okay? Now, what happens here is the following. If you have an electric charge, okay, you accelerate this electric charge, electromagnetic waves go away. Some kind of energy is carried by electromagnetic waves, and this charge actually loses its kinetic energy, eventually stops. For example, an X-ray is created, a high-energy electromagnetic wave is created when you take an electron, accelerate it, and then stop it really fast, okay? That's how you get X-rays. Photons come out, okay? Now, it turns out gravity is a little bit different than that. When you have two really massive objects, let's say the Earth and the Sun, okay? This is the Sun, this is the Earth. They rotate about their common center of mass. So there is some kind of acceleration. Let's say this is the acceleration, right? Towards acceleration of the Earth towards the Sun, let's say. Okay? So the Earth is an accelerating mass. Then it actually loses energy. And eventually, just like an accelerating charge stops, an accelerating mass radiates curvature, changing curvature, ripples in space, going from one point to another point, and then it actually merges with the central object. But for the Earth system, this is so tiny that it is like 200 watts, okay? The gravitational radiation radiated by the Earth and the Sun system is so small that we don't care. We cannot detect it. Okay. But it turns out there are more massive objects moving really fast, and they can create a lot of gravitational radiation. These are called like binary compact objects. You might have heard that in 1975, Taylor and Hulse actually detected a neutron star system. There are two neutron stars. One of them is observable, by radio waves. Okay, so neutron star 1, let's say neutron star 2. So these are really, really, really dense objects. They are as, massive, they have twice the mass, almost, let's say, 1.4 times the mass of the sun, but they are as large as Week2, basically, 10 kilometers in radius. Huge, dense objects. They are rotating about each other. Okay. They can see one of them by radio waves. It emits radio wave because they accelerate charges around when they rotate, and then they can detect the existence of the neutron star. They cannot directly see the neutron star, okay? They can detect that there is one neutron star rotating another one. Now, they looked at this neutron star for a long time. They observed that they are approaching each other, okay? They are approaching each other, meaning their period is actually changing in a tiny amount. How tiny? Well, it is like 30 seconds decrease in 40 years. Okay? They have been observing this. 30 seconds decrease in 40 years. How is that possible? Well, it turns out, because these really massive objects are moving fast around each other, they actually radiate away gravitational radiation. If you wait 300 million years, they will merge, according to theory. The gravitational radiation they actually emit is not detectable on Earth because this is still small, okay? Meaning that our equipment is not sensitive. This is not the gravitational radiation. So these people observed this. They explained the observation, and they got the Nobel Prize in 1993. So this is also something established. Now, for the first time this year, last year, in September, we have seen even something more amazing. We have seen objects which are more massive than neutron stars, black holes, okay? So black holes are essentially burned out stars collapsed to basically nothing that we know. We know what exists basically in the neutron star, sort of. We know that there are neutrons, there is no atom, basically. There is no volume occupied by the atom. Electron falls onto the proton, it becomes a neutron. So you have like a large nucleus, okay? I see neutron star basically as a large nucleus made of lots of neutrons. Well, I mean, uncountable, a lot of neutrons. But the black hole is more than that. Well, even less than that. I don't know how you call it. You take a lot more massive objects, and then it collapses. There is nothing to sort of stop the collapse. There is no internal pressure. That is actually possible to, outcome this collapse, and it collapses into something that we don't know what it is. Eventually, the picture is as follows. So here is the picture. There is a part of space-time, let's forget time. There is a part of space essentially like a prison, infinitely confining prison here, and all the matter, whatever that is, in a form that we don't know, collapse into essentially nothing. So here, if you enter there is no way out, you probably end up in singularity. And the distance from here to there is really small. For example, if the Earth could become a black hole, it could be like this, okay? Erik kadar, it's really small, okay? If the sun could become a black hole, it could be, this could be like 3 kilometers. So there are these objects in the universe which are rather amazing. We don't know exactly what the physics is here. We know the physics around here. What we know is that light cannot escape out of these things. And what we know is that by some chance, two of them actually can be formed because there are lots of galaxies, trillions of galaxies, and trillions of stars in them. So the two of them can actually somehow be formed, and then what is rather amazing is two of them can turn around each other like a system and eventually merge. In that case, this is amazing because of the following. Each one of them creates a static universe. I mean, if you sit here outside a black hole, you wouldn't know that there is a black hole there. It's like Newtonian gravity, really far outside. But if they start actually turning around each other, they change the space in a dynamical way, okay? It is pretty much like this. Let's say this is water, pool, house, okay? Which is perfect. Now you put something on it, very gently. The water bends a little bit, right? This is the analogy of static curvature. If you put a particle here, it will probably get closer to this object. But what happens if I move this like this? So I will create waves, right? Waves that travel. Now, the waves that are created here is the distance between any given 2 points. So these waves, let's say these are the black holes, and the wave is actually moving around the space. What happens is that you have 2 points here. These 2 points will actually move a little bit and then come back when the waves pass. Okay? So what we call wave here is the dynamical, changing of the distances. When, on the 14th of September, 2015, when this wave passed through the Earth, every distance changed a little bit, okay? A little bit. Now, so small that we couldn't, of course, detect it. It was detected by the LIGO detectors. And I should explain to you that this is also something fascinating, okay? You have to understand the following. It is not, this is important, some people misunderstand this. It is not the motion of the objects, okay? When the waves pass, they don't move these objects. What happens is that the distance, the space between them stretches. This is important, okay? It's not like particle is, accelerated to there. The space moves and then comes back. The effect of gravity is on the space, okay? On the time also, but let's forget the time for now. So, on this day, exactly what happened was that in the last moments of this black hole merger that appeared 1.3 billion years ago, but it is so far that it came today, or that day. So here, there is one detector in Louisiana. There is another one in Washington. The distance between them is 3,000 kilometers. This is important because you wouldn't know, exactly if there is a signal or there is noise, or as you will see, this is actually something weird. One of these, well, both of them are like this. They are L-shaped, okay? So 4 kilometers, long, actually, tunnels, and you have vacuum, basically pure, essentially almost, there is nothing there. All the hydrogen is taken out, and you have mirrors. And you have actually mirrors here. I will not be able to explain to you all the details, but what happens essentially is that these arms are so accurately measured, and the light travels between them, back and forth. The light they use is so coherent, so amazingly pure laser that, it is it is really, really sensitive. If you move this a little bit, just a little bit, less than the atom, if the distance of this part moves just a little bit compared to this one, when these scattered light, reflected light come over each other, they either cancel or they add up constructive or destructive interference. You probably know from high school. So looking at this interference pattern, you know that the distances have changed. Okay? That is the thing. So this is actually, LIGO means laser interferometer gravitational wave observatory. Using laser and the interference, they can know exactly whether the distance have changed or not. You see, this is okay. This is possible, and they can measure it, and they measure the distance. Essentially, the change in the distance is around 10 to the minus 21. So small, right? The actual change is 10,000 times smaller than the proton's radius. Amazingly small, okay? What is more amazing is the following. Look, by just a weird noise for a 0.2 second, that noise, how do you know that there were two black holes like colliding 1.23 billion years ago? You know their masses, you know their last moments, you know a lot of things. How is that possible? Well, there are a couple of things. First of all, this observatory had this same signal, and then just a little bit later, 7 milliseconds later, it travels with the speed of light. This observatory detected. That's nice. So they knew that essentially somehow the wave actually came from this part, okay? And it went over there. What is more amazing is the following. If you look at the signal changes like this. So if you analyze the signal, what do I mean by that? The frequency, so they can measure so these 2 points, essentially, these 2 points just did this, okay, motion. But what happened was that the frequency of the gravitational wave changed. This is important. The frequency of the gravitational wave changed from, I think, 35 to 250 hertz. And this is actually the most important thing. It's not the frequency, but the change in the frequency. Listen to me. This is in the audible range. It is amazing. If you start, by the way, do you understand why the frequency increased? The frequency of the gravitational wave. Why did it increase? Their rotational radius decreased, okay? And then they are now attracting each other a lot more. Now they can actually send a lot energetic signals, right? And basically, just like the usual electromagnetic waves, gravity waves have amplitudes and frequency, and essentially this is related to how fast they move. It turns out, if the orbital frequency, this is, let's say, orbital frequency is this, twice of that is the gravitational frequency. So if they rotate around 75 times, they emit 150 hertz, okay? Now, if you analyze this, and then if you look at the theory, this is the amazing thing. The theory tells you that the frequency will change with respect to time like that. That's called the chirp signal, okay? The the change in the frequency is important. And then from that, they can calculate how far they are, how far the collision was, what are the masses of the objects. From theory, Albert Einstein's theory, actually, you can detect it. Now, I haven't written any formulas, actually, to you, but I want you to just go away with one formula, which is, because this is in the paper that they wrote, maybe some of you will be interested in that paper. Here is the thing. This is amazing. Look, if you have a detector which just says, chirp, it doesn't say much. I mean, the detector says something. Using theory, you can understand what the hell is going on, right? Theory is the sort of, the theory will tell you more information about that. The signal is a lousy signal. It's just, chirp, that's it. I mean, people expect like Mozart's song or something like that from this billions of dollars of experiment, and it just says, chirp, that's it. Listen to the listen to the signal noise in YouTube or something, you will get disappointed. Really, because it's this. Chirp. That's why all the physicists around the world are saying chirp, chirp, chirp. I mean, that day, if you look at, social. By the way, your class is like that, like, I don't know, doorknob or something. Get excited a little bit. I don't know how to excite you. What happened to you today? Well, something happened. Okay. Yeah? What? I cannot hear you. I don't know. Look, I gave 3 hours of lectures today. This is the 4th hour. Huh? Okay, you are listening. Before the collision? They actually send signals, but they are not detectable. They are actually so the frequency is important, and the amplitude is important. When they get really close to each other, they send more energetic waves. They change the distances more, if you like, and you can detect it. Okay. Look at this formula. This is beautiful. You can derive it from general theory of relativity. Okay? So, speed of light. So, this is called chirp mass. Okay? It is in the paper, but it was derived before. C cube is the speed of light. That's the gravitational constant. 5/96 pi to the power minus 8/3 f to the power minus 11/3 times the change in the frequency to the power 3/5. Now this m is basically the mass of the system that we have. It is the following. Let me write that mass also. Yeah. Let's say you have two binaries. I mean, not just one binary. M is M1, M2, 3/5 over M1 plus M2, 1/5. You see, I find this fascinating. This is the eye of the theory, okay? You look at F, you find how it changes. In this experiment, it changed from 35 to 250 in 8 cycles, okay? And then you go to that formula, you plug it over there, which you derive from theory, that came out of Albert Einstein's mind, that relied on Riemannian geometry long before Einstein lived. Actually, that was formulated in mathematics. Then you get this M, okay? What is amazing is the following. This M is also related to the distance of this combination. How is that? You work out with the theory also. Let me write that formula. Sizi çok uyur gördüğüm için formülü yazıyorum arkadaşlar. This is another way to torture students, okay? So the distance is 5 over 96, C over H0, I will explain what H0 is, F dot over F cubed. Now, amazing, look, F dot you can measure from the chirp, okay? F you can measure, F dot is the change. H is actually delta L divided by L, which is around 10 to the minus 21. So it just means your height that day on that early morning at 9 o'clock changed by 10 to the minus 1, by a factor of 10 to the minus 1, around 25 times in 1 second. And that was detected. Okay, so I think I'm done. Well, I'm not done, but I think you are done. Okay, thank you.
Sağ olsun.
Ya çok yorgunum, kusura bakmayın.